Alright, I'm going to be covering Chapter 12, which is Type Details and Alternative Coding Mechanisms. Alright, well, my screen just went blank. Okay, it's back now. That's weird. We're going to be covering some different primitives, some integer. We're going to be covering actually a lot of wrapper classes, stuff like that. We're going to be covering type and the ASCII table, just lots of different stuff. Now, this was covered somewhat already in the first course, just not in this in depth. So we're going to cover all that. We're going to talk about short circuit evaluation, and that was covered a little bit in 151. We're going to cover it more now. New break statements, again, once again. A lot of these were covered, but they're being covered more in depth. Okay. Primitives are those built in. Those are just regular data types. Byte, short, int, long, float, double char, boolean, stuff like that. Okay. These are, they hold just one specific thing. An integer holds an integer. Stuff like that. Okay. Now, let's talk about integers. There's actually multiple different types of integers. We have byte, short, int, and long. A byte, as it says here, holds 8 bits, or stores in 8 bits. The values are negative 128 to 127. An integer that most of us use, you'll see, stores in 32-bit, holds negative 2 billion to positive 2 billion approximately. Now, the question is, since we always use integer pretty much, are we using the correct data type? Well, yes we are, but what if we don't need a number that goes up to 2 billion? What if I'm creating an integer to store the age of a cat? So what would the correct data type be to store the age of a cat? Well, would it fit in long? Oh, most definitely. Would it fit in int? Most definitely, unless we have a 2 billion-year-old cat. It would also fit in short, and if you think about it, the age of a cat will also fit in byte. So, it brings up the question, why do we always use integer? Well, it's just because that's what we do, okay? All right. Yeah, it's just what the normal programmer does. Is it the most efficient thing? No. If you want to write a program that's very efficient, let's see, I was watching a movie called 21. I think Kevin Spacey was in it. Oh, it's about counting cards. But in there, they're building a robot. And the entire OS has to fit on this teeny tiny little chip. Okay? So if I'm building something that only has a certain amount of memory or storage space on it, would it be important at that point? Most definitely. Think back to the olden days, like the Apollo 13 space shuttle. They say now that our microwaves have more processing power than the space shuttle did. Do you think it was important to them to use the most efficient data type as possible? Oh, most definitely was. Okay. All right. Now with these variables here, you'll see on the bottom line here at number 5, you can actually print out what they can hold. So if I was to write this piece of code, it would actually print out. Actually, let's do that. Let me bring this. Let me have a program up and ready to go here. It's just really has nothing in it. I'm going to do system.out.println. Now you'll see me do that a lot. Oh hush, get out of here, you stupid pop-up. You'll see me do this a lot. Whenever I create statements like this, I complete the whole thing. I put the opening brace, or parenthesis, closing, then semicolon. That way I know I have it. Then I go back and put my stuff on the inside. Like I can put this. Because so many people have an issue with forgetting parentheses, forgetting quotes. If you put them in the right order, you don't have to worry about it. Max value. Now you notice that's in capitals because that's actually a constant. Okay. Now if I run this, there you go. Integer, as it said on the slide, is 2 billion. So if we put some spaces here, it's actually one there, one there. It's actually 2,147,000,000, so on and so forth. Okay. So what's its minimum value? So I'm gonna go over here and put in min. There it is, negative 2,147,000, so on and so forth. What is byte? Now let's go with this max value. Not max, may use max. Oh, you can't do. Oh, that's right. You can't do that for byte. Okay. Some of them you can't do it because you can only do it for the wrapper classes. But you can do it for double. So you can't do it for the primitives. You got to do it for the wrappers. My fault. There's the largest integer you can hold. Now, actually, I'm going to bring. This is for double. Did we even have double on the chart? Well, we didn't have double on the chart, but we'll just talk about this for a second anyway. This is the largest double we can hold. Now I notice it's only 1.7, but if you notice 1.797, 693, and so on and so forth, with E308, hopefully you all know what that means. That's scientific notation. What that means is the decimal point is moved 308 places to the right. So if we took this decimal point and moved it 1, 2, moved it 308 places over here, that's how large we can store. That's the largest number we could store in a double. Okay. Now let's check float. Alright. Okay. So float here is 3.4, so on and so forth, with E38. So it's a lot smaller. Remember, double holds 300 something, float holds just 38. Alright. Actually, while we're here, let me change my font. As I know it'll be easier for some of you to read. Okay, we want Java font. I have Courier New 12. Let's just go to 20. That should make it a little bit easier for y'all to read. Okay, so if we're using the wrapper classes, we actually talked about them before, but if we're using the wrapper classes, like for integer, we can actually print these out using the max and min, stuff like that. Okay, but they're pretty large. Okay. So the default integer constant is an integer. So if you're just defining something with a number, it's going to default to integer. Yes, it's a waste of space, but that's the way it works. Okay. It says to explicitly force it to be a long, then you use the L. Okay, like long, age of planet, so on and so forth. Okay, and you'll notice here they're actually putting the L. Okay, either will be fine. Continue on. Floating point, floats and doubles. Actually, I just showed you those a second ago. I showed you with the min and the max. I think I just showed you the max, but you'll see they actually hold quite a bit. So floats 32-bit, double 64-bit. So floats hold exactly twice as much. Okay. Now they talk about precision here. If you think back to I don't know how many years ago now when they sold the Pentium 66. Okay. They actually had an issue with a floating point issue, and it would do calculations wrong like 1 in every 4 billion times at whatever the decimal place. It was huge. But they went out and actually replaced everybody's processors. So, kind of funny that they do stuff like that. Alright, I'm back. Now, about this whole precision thing. If we were to write a number, like I think I had one here, when I ran this number, you'll see we actually have a whole bunch of numbers here. Okay, this is a, what did we make this one? This was a float. Okay. Now a float, it's the numbers that are not 0. Okay. This is just approximately. So if you look in scientific notation wise, see these numbers here? These are the ones that are not 0. And as I move this decimal point to the right, let me actually write this number out so you can see what this number would be. If I can get them both on the screen. Okay, this number would actually be 34028235 and 1, 2. Let's see. I gotta figure out how many places. Let's see what. Since that's really what the number starts with, you need to move it 38 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 3, 4, 5, 6, 7, 8. Okay, that's actually what the number is. Okay, you can see that it's a very large number, and the significant digits are these over here that are non-zero. Okay, all this other stuff, I mean, it's more accurate to show it this way, but do we really need to? I mean, how many zeros are there? Well, you have to actually go count them. Where this way down here, you know exactly how many zeros there are. So when you write a number like this, like remember double had 308 had an E to the 308, I mean, I'd be putting 308 zeros. How could you possibly keep track of all those? That's why it's easier to write it this way, because this tells us this number with 38 zeros. Just a little bit easier to read, okay? So that's what the whole significant digit thing is all about, okay? All right, floating points. To access floating points, you can go min, normal, and max value, okay? Those are some of the named constants. It says the floating point mid normal is a qualitative difference than min value. Instead of being the largest magnitude, it's the smallest magnitude. Again, what's the smallest number it can hold? Okay. Let's see, for floating points, if you want the largest magnitude, you would obviously use max value, which we kind of did that answer already. All right. When defining floating point, you can put an F. Okay. Actually, let's do this code so we can see it. Okay. I'm going to define three variables. I'm going to call float GPA1 equals 3.22F. Then I'm just going to copy this 2 more times. It's going to be GPA2 and 3. And it's going to be 2.75. And the last one will be 4. Okay, if I try to run this, let's put this up on the screen here. It's not going to like it. Whoops, I made the wrong part too big. I need to bring this up. Okay, I get an error. And if I bring this error down, it says possible loss of precision. Okay, it's basically saying, hey, are you really, you're not defining it correctly. You need to put the F to tell us that the number's an F. Because remember we talked about an integer. The default is an integer. Well, the default is a double. Okay. This statement right here says the default floating point constant type is a double. And when I'm trying to define this, even though we know I'm defining it as a float right there, okay, I'm defining GPA as 3 as a float. But I'm telling it this number, this is actually a constant. Okay, the number 4 today will be the number 4 tomorrow, and the number 4 next week. So that's a constant. So when I'm taking this constant 4.0, it has a decimal point. So the compiler says, oh, that constant's of type double. Okay? And then we're trying to take that double and stick it into a float. If you remember 2 slides ago, a double is 64-bit, a float is 32-bit. So the compiler is saying, hey, you're taking this 4.0, which is a double. Again, it is a constant. Remember, this is just a number we're assigning to be a float. Just because we say it's a float over here on the left doesn't mean it's actually a float. Okay? It means we are going to make a new variable called GPA3, which will be of type float, and we're going to put a value in it. It's the same as if I put char here. You know, obviously it's going to compile error because it's the wrong data type. Okay, but by putting 4.0, it says, oh, right here we have a double, because 4.0 has a decimal point, so it's a double. Like it says here, the floating point, the constant is a double. So we're trying to put a double into a float, and it says, whoa, 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 we can't fit, because this is 64-bit, this is 32-bit. It's just like if I did this. Now, what if I did that? Well, let's just say 4. If I assign GPA3 the number 4, it says, oh, that's an integer. Okay? Well, let's go back a couple slides real quick. Integer. Integers are 32-bit. Floats are 32-bit. So they should fit. So if I did this, it says, oh, there's no decimal point, so this is going to be an integer. So we're taking the integer 4, stick it into GPA 3, and it works because this is a 32-bit integer. This is a 32-bit float. It fits. But since they're the wrong data type, well, it'll automatically convert this to a floating point, but it will be a float, not a double. Hopefully I explained that well. So 4.0, the default constant type up here on this top line above my code says it's a double. So in other words, to get it to fit into a float, you need to tell it, okay, this 4.0 is actually a float. Okay? Hopefully I explained that well enough there. Okay? All right. Okay, big int, big decimal. I don't think we're using it in any of our projects, but I do use it actually in another class I teach. Okay, it says normally that for applications that use numbers that are large magnitude and high precision, the long and double data type should be sufficient. In other words, a double or a long could hold quite a bit. However, If you require anything bigger, you can use BigInteger or BigDecimal. Okay, they have large magnitude, and really the precision is only based on the computer's memory. Okay, and here's an example. We're defining a num down here. So type BigInteger. Okay, and it's saying is equal to a new big integer. Now this is somewhat of a small number. 1, 2, 3, 4, 5, 6, 7, 8. So what is that? That is 12 billion. Obviously it's bigger than what we can hold in other data types. Still not that big, but it needs to be defined differently because our data types can't hold that. Okay. Alright, at least in the integer area. Okay. Integers, remember it was 2 billion. Let's go back to make sure. Integers were 2 billion approximately. So when we try to put this number, which is actually, if we put a comma there and a comma there, it's actually 12 billion. So it's too big, so we have to say big int. Okay, and again, that makes it a very large integer, and it's based on our computer memory at this point. Okay, how about big decimal? Maybe we have our float in our, see, a float holds with 38 decimal places. A double holds up to 308 decimal places. Well, this one has 400 decimal places, so obviously it's going to be too big. So instead of big int, since it's not an integer, we do big decimal. Okay? Alright, so the big int, big decimal classes are defined in the utilities package. Okay? So when you use them, just import java.util.asterisk. Okay? Okay, there's many methods. You can add, subtract, multiply, divide, mod, pow, all that. Because, we talked about a lot of these already. Like, we talked about mod and pow already. Actually, I think we talked about pow for sure. What pow... Normally, it's of type, I think it's double, or, well, maybe it's integer, I can't remember offhand. But, so this one has its own bigger one. And I do a project at my school, which I'm actually going to talk about here in a couple slides, but about RSA, and the numbers are too big. Okay, so you can use big int for that. Okay? Alright. Now, they talk about returning the quotient and returning the remainder. Mod, well, actually, let me do a real quick on what the heck mod is, because some of you might be saying, huh? What is, let's do 7 mod 3. Okay? Equals. Okay, I'm just changing this thing here. So if I was to output 7 mod 3. Okay, this is just text saying 7 mod 3 equals. Okay, what you do is you take this 3 and you stick it in front of the 7 and do basic division. Remember in elementary school you did how many times does 3 go into 7? Well, that's what this is. You take the 3, put it in front of the 7. 3 goes in there twice. 3 times 2 is 6. 7 minus 6 is 1. So the remainder is 1. So we should get a 1 on the screen. And we get a 1. Very nice. Okay. Now what if I did 7 modulus 7? Okay. Well, how many times does 7 go into 7? It goes in there once. Again, we take the right-hand side, put it over on the front, put the little thingy over it. Let's see if I can... I can't draw it on here. But it's the old... I can't think... Whatever it's called. You learned it in elementary school. Basic division. 7 divided by 7. And 7 goes in 7 once. 7 minus 7 is 0, so the remainder is 0. So this answer here will be 0. Okay. Maybe if I did 15 and 4. Okay. How many times you take the 4, put it in front of the 15. How many times does 4 go into 15? Goes in there 3 times. It's 12. And remainder of 3. So even though that's going to be saying the wrong part there, the answer should be 3. Yay! Okay. So that's how modules work. It's the remainder. Okay. And up here we have the quotient rather than the remainder. Alright? Okay. Cryptography. Again, I said I use that in my classes. I actually do have my students have to write an RSA program. Again, not in this class. Totally different class. Okay? Cryptography is used for encryption. I actually have a bunch of lectures over it. And those of you, if you want to see them, I'm going to show them to you real quick. Let me get in here. I have a website, wordpress.rose.edu. I teach at Rose State College. So if you go to wordpress.rose.edu, it's actually where I put all these podcasts before they get copied up to the other places. But if you went into business division and then 2563, That's actually my computer encryption class. And here's some of the latest lectures. Let's see. There's Caesar Cipher, then the course overview, digital signatures, Diffie-Hellman. There's Diffie-Hellman and AES. There's RSA. If you want to know what more about RSA, I have an entire lecture here. Just click on this. It's my assignment 7. It's all about the RSA assignment. Then here's the RSA lecture. There's also a bunch of other ones. You could go watch that. Also, up here, if you wanted to, there's my Java class, by the way. And here's actually the recording I made for you guys last week. And the one for this week will go up there as well. But here's where I put all my recordings, just in case you're wondering where they come from. Alright, but RSA is an algorithm. Proper cryptography. It's Revest, Shamir, and Alderman are the ones who made it. There's actually a book out called Crypto by Stephen Levy. Crypto by Stephen Levy. Excellent book. Read that book if you get a chance. It talks about all these different encryptions, but it does it in story format, and it's really, really interesting. It's a popular cryptography algorithm, okay? And there's actually a link to it, which you could read about if you want, but it uses BigInt because the numbers are too big, okay? All right. And here's actually a program that does. I'm going to pause for 1 second. All right, I'm back here. Now, this is the RSA modulus. Now, with RSA, you have to use P and Q, and you calculate N, you calculate the totient of N, stuff like that. I'm not going to get into the cryptography of it here, but what we're just showing you here is he's using the BigInt class, and he's actually creating two large random numbers, P and Q, okay? Then you use P and Q multiplied together to get N. Then you also subtract 1 from each, so it'll be P minus 1 times Q minus 1 gives you the totient of N again, which is way beyond this class. But since P and Q are both big integers, okay, and you notice they're 512-bit long each, so pretty huge. So you can't just say P times Q. You have to use BigInt. So that's why he's doing P dot multiply Q. So he's actually using the multiply method of the big integer class to calculate N. Okay. And actually, let me see if I can't. Well, I don't need to run it. Just trust me. They're very large numbers. Okay. All right. Now let's talk about the character data. It says most languages, including Java, character values have an underlying numeric format. I actually showed this before. To show you again, in TextPad, if you go View Clip Library, you can actually see them. Like an A is a 65, a B is a 66, so on and so forth. A small a is a 97, and so forth. Okay? Alright. So, we use the ASCII table for that. We actually covered it in Chapter 3. Actually, let me just do some output here so you can, in case you missed that lecture. And I'm just going to output, okay, let's just output the character A, okay? I'm just going to output the character A on the screen, and you get the A. But what if I want the character value, or I'm sorry, the integer value of A, okay? You get 65. What I told it to do is take this character, convert it, I'm typecasting it to an integer. And now I get 65. Now what if I did char over here and 66? I'm saying take the integer value of 66, which we know will be a B. Take the integer value of 66 and output the character value of it. And there you go, you get a B. Okay? Pretty simple stuff there. Okay? So that's the character data type, and I'll show you what happens there. And there's the ASCII table. Again, it is in TextPad up here under View Clip Library, where you can also ask Google. Just type in, actually somebody came and asked me the other day, like, where can I find the ASCII table? So I said, oh, they got this awesome website called Google. And type ASCII table, and there's like 100 billion copies of them right there. There's an image of it. There's tons of them. So, table of ASCII characters, it's very easy to find the ASCII table. Okay, and there's one in the book for you if you need it. Okay, so the character type, we talked about that already. Okay, Now let's talk about concatenations. As explained, you can concatenate a character value to a string with the plus operator, so we can actually add them together. When JVM sees when a string next to a plus, it converts everything to a string. I actually covered this way back when. So yeah, basically, even though these are characters, first and last are characters, we're concatenating them right here with a string, so they actually get converted to a string. Okay. Alright, so be aware that you apply the plus operator to two characters, then you get numerics. Okay, let me show you that. So if I want to output, oops, not the string, A plus B, I get 131. Why the heck do I get 131? Well, I got 65 plus 66. Now, if somewhere in the middle here, I added a string, even though there's nothing here, it still converts it to a string. Now, whoa. Hold on a second. Let me see what I typed wrong here. Hold on. Alright, I actually typed something wrong here. Oh, wait a minute. Somehow I went to the wrong page. Ooh, sorry, changed our page there. I typed something wrong here. I added the string part at the end, but the problem was it saw this plus between the two characters, added them first, and then created a string. So if I do this, now it's going to show the two variables. Sorry about that. My fault. So now I get AB. Okay? So the concatenation works a little bit different with characters. Alright. And it says, okay, yeah, that's good. Alright. Now it says Unicode Standard. The problem with ASCII, it says it's specified up to 128 characters, and there's way more than 128. And again, let me bring in my chart here. Not that one. That's not what you want. You want this one. Okay. And you'll see they start off way up here, and actually this is the ANSI chart. Do I have just the strict ASCII chart? Well, no, I don't. Okay, this actually shows you more than just the ASCII chart. But if we go back to the ASCII chart, it actually goes through 127, 0 to 128, 0 to 127 is 128. Okay. Well, there's more than that. The Unicode Standard has 65,000 because there's a lot more printable stuff than that. Okay. All right. So you can use. You don't have to wait through your numbers. You do use the character code. So Unicode, bigger, but ASCII just makes it easier to use, and you can learn more about the Unicode Standard there. Okay, the second bullet's actually kind of important. It says, unfortunately, console output, which is what we see, doesn't work. Okay, with Unicode, it only supports ASCII because you can't print some of those. Yeah, even some of these characters here. Like let's try to pick one that won't. Well, actually, all these print okay. Great. Well, no, they don't. Some of these will not print, like 208. Okay, if I was to take, oops. I needed my program here. So what if I was trying to output the character value of 208? Okay, we should be getting this funky D. See that right here? Well, let's actually do it and see what we get. We get that. I don't know what that is, but really it's not being printed correctly. Let's try 216. And we get that. Okay, again, 216 should have been this funky O, but we get this other thing. So some of the characters, they just can't output correctly. Okay? Alright. Now let's talk about type conversion. We can convert back and forth. Okay? Promotion and typecasting. Promotion says, promotion is an implicit. Remember when we were putting the an integer into that float? It automatically promoted it to the next higher data type. So the integer was automatically converted to a float. The same with character, converted to a string. But you can also typecast, which forces it in there. It says promotion is an implicit conversion. So when an operator type is automatically converted without having to use a typecast. It occurs when there's an attempt to use a narrower type in a place that expects a wider one. It automatically does it. Okay. So here we go. We have a long and a float. Which one's bigger there? Well, obviously the float. Okay. Then we have a double, Z. Okay. Then we have 3.45, 3 plus 4.5. 3 is an integer. 4.5 is a float. So what it does is it actually converts the 3 to a float, then adds 3.0 plus 4.5. then stores it in Z. Okay? Now the next one, int num, and we have k plus 2. 2 is an integer, k is a character, so it will convert it to the ASCII value, whatever lowercase k is, and then it will add it to 2. Okay? Easy enough there. Okay. Alright, says promotion typically occurs as part of the assignment statement. Okay, here's where they have a float variable here, x. Then they're passing it to the print square thing here. Okay. Then it's outputting the results. Okay, it's just, you'll see the print square method that we're calling receives this value right here and as a number, automatically converts it to a double. So this x initially is a float, converts it to a double. This 3 initially is an integer, converts it to a double, then it multiplies them out as well. So you get doubles both times. Now typecasting, which is what I just showed you a few minutes ago, you can force things into a different data size. So we have a double x, which is equal to this value. Remember, can have up to 308 places, I guess, decimal places. Well, not places, but scientific notation 308. Then we also have integer y. So we want to put x into y. Well, x is a double. Actually, let me type this one real quick so we can see exactly what happens. Okay. So I'm going to say double x equals 1, 2, 3, 4, 5.6. Int y equals int x. If I could spell this correctly. Okay. First of all, will that compile? Well, let's see what we get. It does it because what happens is this double is being stored in x, which is fine. Then we're telling it to take that double from above, convert it to an integer. It actually is stripping off that. Okay. So if I was to output x, we should just get, I'm sorry, let's output x, then let's output y. Okay. If we output x, we're going to get 1, 2, 3, 4, 5.6. If we output y, we should just get 1, 2, 3, 4, 5. Yep, exactly what happened. Because this x is the double, but when we use this typecast to int, we actually chopped off the 0.6. Okay, easy enough there. All right. Okay, here's a program to do it. They're just showing you examples using the ASCII value and the character. Okay, I'm not going to walk through that one because I think we kind of talked about that already. Now let's talk about prefix and postfix, increment, decrement. Again, we did do it in prior classes. Okay, but here's prefix right here, plus plus x. Okay, and postfix is x plus plus. Okay, plus plus x increments the x before it's used. Okay, so y plus plus x equals x plus 1, y equals x. Okay. Postfix x plus plus increments afterwards. Let me show you what the heck I just said. Okay. Let's just say, let's get rid of this. Say integer x is 5. Okay. Just make this simple for us here. So if I output 5, this statement, I should get a 5. I do. Now, if I did y plus plus, actually, let me copy this statement a couple times. Okay. Now I should get 555. And I do, very nicely. So now if I did y plus plus, what should I get? Remember, plus plus is a postfix method. Okay. Increment x after it's used. So I'm saying increment y after I use it. So I should output the 5 and then increment to 6, and then this should say 6, 6. So it should be 566. Yep, sure enough, I get 566 because postfix says use the y first and then increment. So I printed the y, which is the 5, then I incremented to 6, then I printed 6 and 6. Now what if I did plus plus y? Here, what did I get? Well, now I have postfix. Remember, it's going to print out 5 and then increment. So at the end of this statement, it's now got the value 6. Now we're using prefix. Okay, So y was the value 6 at the end of this statement up here. So now we're going to increment it to 7 and then output. So we're going to get 5, 7, 7. In theory, let's see. Let's see if I screwed it up. Nope, 5, 7, 7 perfectly. Okay. So again, prefix. I'm sorry, this is postfix. Mix them up. Postfix. Use the value first and then increment. Prefix, increment first, and then use the value. We actually do this in assignment. I think you actually did it at the beginning of this class or the end of last class. I can't remember exactly which one. I think it was the end of last class. All right. There's examples of both of those. All right, here are some more examples. Traces codes fragment. Well, I just walked through my own, but we'll walk through it. X is 4. Y is what? Well, since it's prefix, y becomes x plus 1. So y is now 5. So we'll output 4 and 5. Then we'll say x is 4. Y is x plus plus. So it actually is going to do the same because it's going to, this statement ends, so it's in an increment as well. But all right, I think I kind of explained that pretty well. All right. Decrement, same thing. But instead of plus plus, now we use minus minus. They're still prefix postfix, work exactly the same. So I'm not going to walk through those, but they work exactly the same as the prefix and postfix. They're just decrement rather than increment. Okay. Now let's talk about precedence and evaluation. Okay, this is operator precedence. Actually, let me pause just for a second. All right, I'm back. All right, this slide is a little, can I say, advanced for this area. But what it does is it replaces them. So first of all, what you do is you replace the y right here with a 3. So you end up with 3 plus, and so it'll be 3 plus, then plus plus y times y. So it'll be 3 here plus, and this actually gets evaluated to a 4 because remember it's prefix. So it's 3 plus 4 times 3. Okay, and I think that's the only one that got there. Actually, no, because this is first. So it's 3 plus, this changes it to a 4 times 4. So it's 3 plus 4 times 4, and it ends up becoming 19. Okay, again, because this is a 3 right here, plus, then as soon as we hit this, it goes left to right. The plus plus y changes the 3 into a 4. So it's 3 plus 4. And since y is now a 4, remember it just doesn't output a 4. It actually changes its value. So this ends up becoming a 4. So y is a 4 times 4. So it's 3 plus 4 times 4. 4 times 4 gets evaluated next. So it's 16. 3 plus 16 is 19. Okay? That's, again, it says there both these are equivalent, but it goes left to right. But hopefully you got that. It's a little tricky, but not all that bad. Okay. Now let's talk about embedded assignment operators. All right, now let me talk about this embedded assignment. Now the way assignment operators work, it's always like the right to the left. So this is saying B is equal to 8. So 8 is assigned to B. 5 is assigned to C. So what does this statement do? A equals B equals C. Well, C, remember assignment operators, you always start on the right, just like the 5 is equal to a C. So since C is equal to a 5, so B equals C, so this is a 5, so this 5 gets assigned to B. So then we have A equals B equals C, so that becomes 5, so A equals 5. So then, since B became a 5, then A becomes a 5, so when we get this print line, A, B, C, we end up with 5, 5, 5. Again, assignment operators always go right to left, just like you see here. The 8 is assigned to the B, the 5 is assigned to the C. This statement works the same way. Since the C, initially, again, that's an A, that's an 8, that's a 5. So we're saying 5 is assigned to B, so B now becomes 5. And then this 5 gets assigned to A, so all three of them end up being 5. All right, and here's an example walking through it. Feel free to walk through it. Again, I just showed you that example. It's not that difficult, but it is there for you if you want to walk through it. Okay, now let's talk about conditional operators, also known as ternary operators. I think he might mention that here somewhere. Okay, it's a way of doing an if-then-else all in one statement. Okay, you do condition, true or false. Okay, so we have here, x is greater than y, x or y. Okay, it's called a ternary. It has 3 parts to it. Okay, so it says assume x is 2. What does the expression evaluate to? Okay, so let's see, x is 2. Is x greater than y? Okay. X is 2, so the answer is false, so we end up with 5. Okay? So if we were assigning this somewhere, we're saying if x is greater than y, if it is, then true go x, false go y. It's false, so we end up with 5. Okay? So again, conditional operators, it says, implements an if-then-else logic using a more compact or one statement. I've actually done this many a times. If it's true, the condition evaluates to the first expression. If it's false, it goes to the second. So if this condition is true, evaluates to the first. If this condition is false, it goes to the second. So this condition is false, so we end up with y, which is 5. All right. So it says the operator expression could not appear on the line by itself because it is not considered to be a statement. Again, it's really nothing. I mean, if you look at this statement right here, we're basically saying if this is true, then this or this. Okay, it's just like saying 5. You can't just say 5. So here in their example here, what they're doing is saying the grade is equal to, okay, actually let's go up here first. They're calculating the score. Score plus equals, this is a compound operator, hopefully you remember that. Score is equal to score, which is 58, plus the evaluation of this statement. Okay. So this says extra credit. Again, it's evaluating the condition, and the condition is true because extra credit is true. So condition is true, so we get a 2. So score equals score, which is 58, plus this evaluates to a 2 because that's true. So score is now equal to 60. Okay. Then we print grade equals score greater than or equal to 60. Okay, so what is score? Score is 60 because remember this was true, so we added 2. So score greater than or equal to 60, yes, so we output pass. Easy enough, okay? If extra credit was false, then we say score is equal to score, which is 58 plus. This evaluates to 0, because if this was false, again, if this was false, we would get a 0. So we end up with 58. Then we say score is greater than or equal to 60. That would be false, because it's only 58. Again, this is true, this is false. So we print fail at that point. All right. It says using a conditional operator, okay, and not the absolute value, write a one-line code fragment that implements this pseudocode. Hold on. All right, so let's write some pseudocode. I'm going to write it in my program right here. Okay. The way it starts, first of all, we have x, and this is pseudocode, it's not Java. So this first part says this value is being assigned into x. So x equals, okay, now we got to do the absolute value of y. So, yeah, I'm going to write that for you. So it's y is less than 0, question mark. Then if it is, it's negative y or colon y. That's actually the code for it. So x is equal to y is less than 0. If it's true, it's y, or else it's y. Negative y, or else it's y. Okay, that's actually the way you do it. Not too important that you understand it at this point. Okay, let's continue on. Evaluate the following expressions. 5 plus 6 plus 7 plus 8 plus 9. Okay, so we start from the left. 5 plus 6 is 11, plus the string 7, plus 8, plus 9. Okay, so now we're going to add 11 plus 7. Well, what is 7? 7 is, let me find it over here, 7. Bring my ASCII chart back up. 7, since we're using the string array character 7. So 7 is 55. Okay. Wait a minute, you know what? Oh, my fault. My fault totally. Hold on. No, my fault. Don't even bring an ASCII chart at this point. That's a string, not a character. So it's 5 plus 6 is 11. So 11 plus 7, so we end up with 11 plus 7, but since this is a string, that 11 gets converted to a string. So now we end up with, actually, let me write it up so you can see exactly what we get here, since I can't write on the board. 5 plus 6 is 11. Plus 7 plus 8 plus 9. Okay, we're at that point. So 11 plus 7 actually turns into this. 8 plus 9. Okay, this turns into a string because we took an integer, but we're adding it to a string. Remember we talked a couple slides ago, whenever you use concatenation, it actually converts it all to a string. Okay, so now I got 117 plus 8, same thing, except it's on the other side. So now we end up with the string 1178 plus 9. Then we end up with the string 11789. Okay, easy enough to do. Okay, I'm not going to walk through all of them, but that's pretty much how you do those. Okay, this bottom one, 5 plus 6, would be 5. Actually, let's put my thing back up here so you can see it. That would be 5 plus the character 6. The character 6 is 54. So it would be 5 plus 54 would be 59. Okay. This other one, you use the character 5 plus the character 6 plus the string 7. So this would convert to a number. This would be converted to a number. They would add together. Then you would convert it to a string, so on and so forth. But we're not going to walk through that one. All right. Okay. Wow, we've got a lot of practice on this. Assume integer x is 6, y is 4, double z equals 10. Evaluate the following expressions. Okay, so z minus x divided by y times 4. Okay, so z is defined as a double. We see that up here. Okay, 10. So we got z minus x. Okay, well this 10 is an integer. Remember, it's a constant, so it's an integer. But since we're assigning it to z, which is a double, that actually becomes 10.0. So we actually have 10.0 minus x, which is a 6. We have 10 points. Let's see if I can write this down. Make this a little bit easier for us. So we have 10.0 minus 6 divided by y, which is 4. Okay. Times 4. Okay, we're there. Times 4. Alright. Now that is all in parentheses. Okay. Then divided by 4. Okay. That's what we got so far. Okay. So we got 10.0. Now what's the next step we do? Okay. 6 divided by 4. What is 6 divided by 4? Well, 6 divided by 4 actually comes out to 1. Okay. Oops, sorry, that actually comes out to 1. That goes over here. So we end up with 10.0 minus, now the 1's in the wrong place, minus 1 times 4. Okay, and this is all inside of that. Okay. Divided by 4 again. Then we get 10.0. So we got, this is still in parentheses, 10.0. Okay. Now, since we have minus 1 times 4, we actually do the multiplication first. So we multiply these out. So we don't end up with 9.0 times 4. It's actually 1 times 4 is 4. So it's 10 minus 4 in parentheses again, divided by 4. Okay. Now inside the parentheses we end up with 6.0 divided by 4. Okay. Now since they're the different data types, they do convert to double. You end up with 1.5. Okay. And just to clarify, this up here becomes a 1. Why? Okay. Why did this become a 1 and this become a 1.5? Well, there's a good reason for that. Since these are both integers, we're doing integer division. Okay, how many times, 4 go into 6? Because it's done one time. And since we're working with integers, there's no decimal places. So 4 goes into 6 one time. So that's why we get a 1. So 6 over 4 becomes 1. Okay. Now 6.0 divided by 4, since this is a double, or a floating point data type, this becomes 4.0. 6.0 divided by 4.0, end up with 1.5. Okay? Easy enough? Alright. We're not going to go through the rest of these. Alright. Oh, are those the same answers? Wow, he's got tons of them. Sorry, I'm not going to go through all these. Alright, if you have questions on those, ask me. It's just going to take too long if I want to go through all of them. This recording will be forever. It's already over an hour. Okay. Short circuit evaluation. Okay, the following code fragment calculates a baseball player's shooting percentage and prints an associated message. What happens if the code runs with inputs 0 and 0? Okay, actually I covered short circuit evaluation in one of the prior lectures. I can't remember which one, but we're going to talk about it here. Okay, so we have number of shots attempts as our output. Then we're getting an input for an integer into attempts. The number of shots made, we're getting another integer input for made. Now we say if attempts is greater than 0 and double made divided by attempts, okay, is greater than 0.5. All right, so on this one here, let me explain something to you. The way short circuit evaluation works, okay, see this and sign? Actually, let me bring in my little thing here so I can write you something here. If I have true and true, the answer's true. Okay? If I have true and false, the answer's false. If I have false and true, the answer's false. If I have false and false, the answer's false. Okay? With an and, like this, okay, both sides have to be true for the answer to be true. Okay, the rest of these have a false in them, so the answer is always a false. Okay, well, the way Java handles that is, if it's reading through here and it finds a true, okay, then it checks the right-hand side. It says, okay, they're both true, so we're true. It checks this true, so it checks the right-hand side, and it's a false. But with Java, if it reads the left side and it finds a false with an and sign, okay. So if we start off with a false and we have and, do we even need to look over here? Okay? Because remember, for an and sign, they both have to be true. So if we have a false, we don't even need to look at the right-hand side. So you notice both of these with false at the beginning end up false because the right-hand side really doesn't matter at that point. That's the way Java evaluates. Okay? So up here we have if attempts is greater than 0 and something. Okay, so what if my attempts is let's say my attempts is 1. Okay, so if attempts is greater than 0, if my attempts is 1, obviously that's true, so we need to evaluate the right hand side. But what if my attempts is 0 or less than that? I mean, it'd be stupid if it was, but so if attempts is 0, okay, do I even need to evaluate this right-hand side at all? If you think about it in basketball, if I haven't made any attempts, then why would my percentage be? Okay, but if attempts is greater than 0, if this statement evaluates the false, with short circuit evaluation, I don't even have to look at the rest of it. Why should I care? Okay, why should I care? Okay, then oh, by the way, to print a percent sign, you need to have double percents, but we've actually talked about that before as well. Let's talk about it a little bit more on the next page. Okay, the expression and or is evaluated like that. Okay, all we do is we check true or false. That's it. So for the and, short circuit takes place with the left as a false. So if the left is false, just like I showed you here, if the left is false with an and, do I even need to look at the right? I don't have to. And Java knows that. Java says, you know, if the left is false, why look at the rest? Okay? So basically it skips it. Okay? Now, with an or statement, what if I had true or true equals true? true, or false equals true. False or true equals true. False or false equals false. Okay, now these are ors here. Okay, now with ors, all we're looking for is a true anywhere for it to be true. You notice that? If we have trues on both sides, trues on the left, or true on the left, they're always true. Okay, so if it sees a true on the left, does it even have to look at the right? No, it doesn't have to, because with an or, this is an or, doesn't matter. So true or true is true. True or false is true. So if it sees a true on the left with an or, it stops even looking, because it already knows the answer is true. Okay? Got that? So if it's true on the left, okay, and we have an or, then we don't even have to look at the right. Okay? So short circuit takes place when the left has a true on it, so it stops looking at it. So what's the benefit of it? It's faster. Okay? The benefit of it is that it's quicker. It is just quicker. Okay? This is to help also problems by enabling you to avoid illegal operations on the right-hand side of the expression. Especially if you're doing something maybe like dividing by 0. If the certain number is 0, you obviously don't want to divide by 0, so you really can check the left side. Actually, let's go back one slide for a second here. Let me go back one. Okay. This one here, see we're dividing right here? So what if attempts was 0? Okay. And we tried to evaluate this right-hand side. Then we would be dividing by 0. You know that whole thing, you can't divide by 0? You can't spit in the wind, tug on Superman's cape, or divide by 0. I think it's a Jim Croce song. Okay. So, you cannot divide by 0. You can't do it. So this here will prevent that. Because if this is less than, if it's not greater than 0, short circuit evaluation basically says, oh, don't even bother looking at the right. Okay. So it really can help us prevent that. Okay. Then they talk about here printing a % sign. Okay. Okay, and that. Okay, good. Next. Okay, now let's talk about empty statements. Okay, an empty statement is a statement that does nothing. Makes sense. Okay, it's a semicolon by itself. It is a complete statement. It's just empty. Okay, so use the empty statement in places where the compiler requires a statement, but you don't need to do anything. Okay, so with our for loop, we need some sort of statement after it. Okay, just put a semicolon. Done. Okay, you don't have to worry about it. Okay, maybe this, I guess, is a delay. Okay, yeah, this is actually making a delay. It's whatever, making the compiler run through this loop, what, 1 billion times? So it's actually going to make a delay. But the for loop requires a statement, so you actually could put it after it. You could also put the semicolon up here at the end. It would both work exactly the same. Okay? So empty statements can sometimes be useful, but they can also lead to cryptic code. Okay? So the programs sometimes accidentally introduce the empty statement to a program, and actually not just programs, sometimes students does it by putting one somewhere. It's like this while loop right here. By putting this semicolon here, it basically stops our while loop. It never even checks down in here, because that's the end of it. It's the same with our for loop. If I put the semicolon at the end of a for loop, it kind of ends there. Some of you will put a semicolon at the end of your method headers, and you'll get an error, something like, actually, let me try to write one of those real quick for you, just so you can see, because a lot of you end up with this error. Okay, so we have our method. I'm going to make another method. Public, static, void, SOP. Okay, just a method. It really does nothing yet, but it's a method. Okay. Well, if I go up here and I accidentally put a semicolon at the end of it, I'm going to get an error. The reason is, okay, this method, again, this is the body for the method, but when I put this here, it says, oh, that's the end of my statement. Well, there's no body right here. It's looking for a body right here, and it can't find it. That's why it says, error, missing method body or declare statement. Because it saw this semicolon, and it thought that was this, and it says, where's the body? You didn't give it to me. So if you remove that, it fixes your problem. Okay, so that's an empty statement. Alright, let's continue on. The break statement within a loop. Pause for 1 second. Alright, I'm back. You know what? Actually, before we get into break statements, I'm going to go back here for a second. One thing I forgot to mention, which I don't know if it's in the book or not. Remember how I talked about shortcut evaluation checks the left side with an and if it's false, it already stops checking it? Well, you can prevent that. If you use a single and sign, let me show you what I'm talking about here. Get rid of this. If I was, let's see, if I was to do true and false, remember that? Equals false. Well, if I did false and true equals false, the moment it sees this false and this and, it stops. That's called short circuit evaluation. Okay? But if I wanted to force it to check both sides, I could. I could actually do it like that. If you use a single and sign, or ampersand, it will evaluate both. It'll say false and true. I mean, it'll still give you the same result. But if you want to force it to evaluate both sides, you can just use a single one. Or if this was an or sign, if you use a single or, it would evaluate both sides as well. I really can't think of a good answer for it. I mentioned this in one of the other lectures. It's not really valid, but my point is maybe I'm in the hospital and I'm dying or something, and I'm not breathing, but my heart's beating. I don't know. I mean, if I'm dead, I would rather them check my heart rate and to see if I'm breathing rather than just my breathing. You know what I mean? I'm one of those things I would hope someone would take the time to check out all the parameters of me. And what if I had a computer determine if we were dead or not? Okay? And it used short circuit evaluation. Oh, his, whatever, he's not, or his heart's, yeah, how about this? So short circuit evaluation. On the left side, we're checking heart rate. Okay? Okay. Well, the heart's not beating because maybe I'm in the hospital having surgery and they're bypassing my heart. Oh, his heart stopped beating. He's obviously dead, and then they throw me in the hole. Not a good plan. I mean, it's a stupid answer, a stupid example, but point is, you can require it or cause it to check both by using just the single one. Okay? All right, now let me continue. I was on break statements. Okay. We actually talk about this a whole bunch in the prior class as well. It says it terminates an immediately enclosed loop and gives control to the next statement. What does the program on the next slide do? Well, we'll look. It says don't follow and trap using the break statement too often. Normally you will see it inside of a switch statement, but not too much other than that. It says usually someone's reading your program will look only at the loop heading to figure out how the loop terminates. They won't look at the break. And normally you see it only in a switch. Okay, if using a break statement, you force the reader to look inside the loop. It's kind of like, when someone's reading a book, if I get a new textbook and I want to see if it's any good, do I sit there and read the entire book? Well, no. I normally look at the chapter, table of contents. I look at some of the chapters, but I don't go through the whole thing. With a break statement inside your loops, you're requiring them to go the entire thing. Okay, so here we are. If I look at just the for loop up here, the for loop heading, okay, day 1, day less than or equal to 90, increment. So I know I'm going to go, actually, what is this program even about? It has something to do with money being invested, okay? Starting at day 1, going up to day 90, increment each day. So this loop is going to go for 90 days, okay? But if you look inside, okay, it's checking if you have no money or you have over $5,000. So it's really checking those conditions. And if you have no money or more than $5,000, then it breaks and gets out of the loop. Okay? Kind of like my checking account. My checking account gives me a higher interest rate than normal as long as I have money and as long as I have less than $25,000. Anything above $25,000, they don't give me the higher interest rate. So that's where you could actually have, if balance is greater than $25,000, break, and it won't give me the additional interest rate. Okay? All right. Enumerated types. It says enumerated type is a programmer-defined type that is used to restrict a variable to holding only a fixed set of values. So suppose you're working on a program that needs to keep track of the days of the week. An elegant solution would be to find a day enumerated type like this. And we can put in Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Okay, very easy to do. Okay, it says after day is defined, you can then use it just like you would a other class. So it's public enum day. So now we can say day, Friday, whatever you want. It'll be very easy to do. Okay. Grade management program. Okay, we're actually way too long on this lecture, so I'm going to try to finish up here shortly. Actually, let me pause for 1 second. Alright, I'm back here. Okay, in this program here, he's actually assigning some grades. Right here, we have a enumerated data type called grade, which is going to be F, A, B, C, D, so on and so forth. And he uses it throughout the program. Again, I'm not going to walk through this whole thing, but it does, he actually can check it now because it actually is a data type. Okay. And since he's switching on grade, see right here, makes a new data type called grade with a big G. He's saying small grade is of type big grade. So then we're switching on grade. So we're switching on the actual grade, which is A, and you'll notice he has a break statement in there. And let's see if he uses it right. And right here, he can check it if grade is equal to grade.A, so on and so forth. Else if percentage is equal to whatever, then grade is equal to grade.B. Else grade is equal to grade.C, so on and so forth. So you can actually use your enumerator data type just like a variable that way. It's actually kind of handy. Okay, you can compare them as well. Okay, if grade is equal to, again, this is the relational operator, not the assignment operator, because it's double. Okay, so if grade is equal to grade.f, so we're checking your current grades. If it's equal to an F, then this is a required course. You must retake it. Hopefully that's not any of you in here. Okay. All right. Ordinal. Let's talk about ordinal for a second here. Ordinal position is like, right, actually, I'm going to go back to where we defined this grade originally. Okay, this is position 0, so grade ordinal 0, ordinal 1, 2, 3, 4. So they're in order of F, D, C, B, A, backwards. So here they're checking if grade.ordinal, in other words, whatever grade they got, if the position of that is less than the grade C's position. So again, this is going to return an integer. Okay, and C's position would be 0, 1, 2, since it's the second one. Okay, so if the grade is less than 2, this is a required course. So, okay, that's what the ordinal does. Okay, enumerated data types as a class. All right, you can use an enumerated class as a enumerated type as a separate class. You just do it with .java. You compile it to a .class. Okay, now there's a difference here. Okay, we always talk about when declaring variables, we always say make them private, but when you're actually as a separate class type, you should make them public so people can access them. Just like on this example, we were checking grade.c or grade.f up there at the top. If that data type or if that enumerator type was private, we wouldn't be able to access it. So what you want to do is, let's go back to it again. Okay, see how it's private here? Private type. This is only available inside this grade management class. If I wanted to be able to use this in a separate class called grade or something, I would need to make it public so that so that people could use it. So if I'm in a separate class called grade, I would want to make it public so people could use it. But then I would want to make it a constant so no one could change it. So I'd probably make it public and a constant. Okay, that's pretty much what they talk about here. Okay, here's the enumerators in the cities. We have the city class, which has the different cities inside of it. And I'm assuming that's the longitude. The distances between them. Okay, all right. And then it's actually a separate one which you can use. Okay, and I think he's going to call it here. Where's he going to call it? Come on. Here's where he actually is going to use it. Now he's actually saying city. Remember, city is the type. City is the type you defined on the last program. And origin equals city.parkville. And again, let's go back and look at it. City was the enumerated type. but it's actually a class called city.java. Okay, and we have Parkville. So the city Parkville is a enumerator type in the class city. So we can use it here, city.parkville, city.kingston, so on and so forth. So they can use it, okay? And you can use it to calculate the distance between them, okay? We're not going to walk through it in great gory detail. All right. Retrieving all the objects of a data type. Says you can retrieve all the objects by using the value. Okay, so city, right here, city, city. Remember that this is the for each loop. It says for each element of type city in city, do something. Okay, so for each city in city, I want to see their values. So this will print out all of the cities. It would print out, where are they? Parkville, Havana, Kingston, NASA, so on and so forth. Okay, all right. Okay, binary, hex, and octal numbers. Okay, I actually use this a bunch of my encryption programs as well. Binary is 0 and 1. Octal uses base 8, so 0 through 7. Hexadecimal goes through 16, so on and so forth. Okay. This is binary is just symbol 0 and 1. Base 16 or hexadecimal is 0 through F, like he says here. In Java code, you can use 0B, 0 or capital B for binary, or 0x for hexadecimal, so you can very easily specify. And we can see an example here. Number conversions. I actually wrote many Java programs that do this, actually. Okay. Okay. Here we are specifying binary numbers. Okay. Hexadecimal numbers. Decimal numbers. So it's actually outputting the different results there. Okay. Let's see. I don't know. Okay. This is decimal here. That's binary. We know about the X. So decimal, I'm not binary, I'm sorry, hex. Decimal to hex. And here we're doing binary to hex, binary to decimal, binary to octal. Okay. Then we have integer to string. So down here we're doing hexadecimal, decimal to hexadecimal. Okay. Then we are doing decimal to octal, and then the last one is decimal to binary. Okay, all right. I know it's kind of weird, but that's how it works. Again, these are the see this whole integer to string thing here. We take our integer, and we're telling it in base 16, base 8, base 2. So it's hexadecimal, octal, and binary. Okay. So it's decimal to hex, decimal to octal, decimal to binary. Easy enough to do. And there's what the outputs look like right down there. Okay? Alright. We're not going to walk through this, but it is in your book. You can look at it. And it'll actually, I think it's in there. We can even run it. It's a little program he made. So, alright. Where's question 1? Okay, question 1. Oh, for some reason it's on the next slide. Okay, let's do question 2 first. If an expression uses the double AND operator and the left side is false, so again, we're using a shortcut evaluation. The left side is false. The entire expression evaluates to false without bothering to evaluate the right side. Which is this? Oh, I already said the answer. Sorry. Which is this example of? Shortcut evaluation. We talked about that. Remember, I mentioned if you want to evaluate both sides, you can still use this single ampersand. So again, shortcut evaluation. Okay, now 1, again, I don't know why 1's second, but it's okay. Alright, what is it called when the plus plus operator is to the left of a variable with plus plus x? Okay, that's called prefix mode. X plus plus is postfix. Okay, it's also called unary operators because it's just one operator. Okay, and I think we're done. Oh, no, there's another question. Why isn't the question showing up? Oh, there it is. Okay. A semicolon by itself is a legal Java statement. What is the name of this type of statement? Is it an empty, closing, or exit? It's actually an empty statement. Alright, that's the end of this chapter.